No, wait. Secondo me non è questa, is not this one. No. Okay. Okay. Yeah. So the velocity component U is much bigger than the V component of the velocity, and also for the gradient, velocity gradients, the gradient of the U component of the velocity in the Y direction is much bigger than the gradient of the velocity U component U in the X direction. That means that this component U of the velocity change a lot in the Y direction and in a negligible way in the X direction. If you go back to the shape of a velocity profile, of a velocity U profile inside the boundary layer, you can recognize immediately this behavior. The V component of the velocity is very small, and its gradients in the X direction and in the Y direction are nearly negligible. Concerning the temperature, the same. That means the temperature gradient in the Y direction is much bigger than the gradient of the temperature in the X direction. And again, if you go back to the shape of the temperature profile inside the boundary layer, you can recognize this behavior. So the temperature change in the Y direction, because the boundary layer express the temperature change in the exactly in the Y direction. Due to the assumption related to the velocity gradient, we can obtain the final expression for the viscous stresses. In particular, okay, keep in mind the velocity gradient assumption. If we go back to where I express here for the Newtonian fluids the viscous effects, you can see that all the expression in the sigma xx and sigma yy expression are negligible, because this one is negligible, this one is negligible, this one is negligible, and also for the other component. So sigma xx and sigma yy become negligible. The unique expression for the viscous effect is the shear stress, so the tau component that become equal only to this gradient, because this second gradient in the bracket is negligible. So I go back to our slide, and finally the shear stress is only me that multiply the gradient of U in Y. This is the explanation for which at the beginning of this long chapter in the definitions, I say to you that for a Newtonian fluid, the viscous shear stress has this expression, because this expression comes from the application of the boundary layer approximation. And now I have to apply this list of approximation to the equation obtained previously. And continuity equation, I have that both the contribution, both the derivative are very small, and is verified, the continuity equation. The continuity equation can be maintained as in the original formulation, because the two derivative, the two gradient are in the same order, are very small above. the change is in the momentum equation. So I come from this one, this expression, and I apply the boundary equation. I do another assumption. I consider for steady flow, steady state flow, for which the derivative of u is in the time, in tau, is negligible. Obviously, you must be able to convert this expression with the substantial derivative in the derivative that are included in the substantial derivative. So the steady state flow allows us to neglect the derivative in time. And in the second member of the equation, I recognize immediately that I keep only, for this second derivative, I keep only the second derivative of a u component of the velocity in y. The original formulation includes also the derivative in x, but I know that the derivative in x is negligible. So I keep only the derivative in y. I do another assumption, so additional assumptions are steady state flow and negligible force and negligible body forces. So we neglect this contribution of capital X. If you go back, you can remember that capital X means body forces. For us, body forces are typically buoyancy forces that are relevant when we consider for natural convection. So neglecting the body forces, neglecting capital X, means that we are writing the forced convection equation. In forced convection, what means forced convection? Forced convection means that the motion of a fluid is due to an external equipment, for example, a fan or a pump. If I'm in forced convection, I can neglect the capital X component of the body forces. And so I neglect this term. And I keep only this light blue equation. This is for the x direction momentum, because for momentum equation I have two equations, one for x and one for y. Now I have to analyze the y equation. If I express all the term of the y momentum equation, I can do the same type of analysis, considering the velocity gradient, considering again a steady state flow, and considering negligible y, capital Y, body forces, and I obtain only this expression. So I can simplify, I can neglect all the terms in the y direction momentum equation, keeping only this derivative. The y momentum equation is simplified, obtaining only this derivative of a pressure in the y direction equal to 0. It's important, this final expression for the y momentum equation, because it gives us information about the behavior of a pressure inside the boundary layer. Remember which is the axis that we consider. Y is the direction normal to the plate. If I say that dP, the pressure, the derivative of the pressure in the y direction is equal to 0, means that the pressure does not change in the y direction. Means that the pressure inside the boundary layer depends only on y. Means that keeping the same x, the pressure inside the boundary layer is exactly equal to a pressure outside the boundary layer. Okay? I go on. If someone has question, stop me and I repeat. So if a pressure depends only on x, I can write P is equal only to as a function of x, and in the momentum equation, that is this one, I can substitute the partial derivative of pressure in x with the total derivative of pressure in x, because pressure depends only on x. This will be important in natural convection, this point. That means that if I know that the pressure does not depend on Y, means that if I know the law for the pressure as a function of X outside the boundary layer, the same law is valid inside the boundary layer, because in Y direction the pressure does not change. And an additional observation, yes? I can hear you. Wait, I can hear you. You have problem with your microphone, I think. I can hear you.
No, I have a question, but if you want to explain it, okay, I wait.
Write on the chat, because I can hear you.
Okay, Professor. Okay.
Wait. If you do not write something, I don't know your question. I go on. Okay. I can. And so this one, saying that the pressure does not change with the Y direction, means also that if the external pressure is constant, so if outside the boundary layer the pressure does not change with X, also inside the boundary layer the pressure does not change with X. So if, for example, if I consider exactly this case with an horizontal flat plate, I can assume that the pressure does not change with X outside the boundary layer. Immediately, I can deduce that also inside the boundary layer, the pressure does not change with X, and I will simplify it in the X momentum equation. Now, I have to analyze the final third equation, that is the energy equation. The energy equation involves also temperature, so I have to use this approximation for the derivative of temperature in Y that is much, much bigger than the derivative of temperature in X. And I simplify again steady state flow, and again in the second member I keep only the derivative of temperature in the Y, the second derivative of temperature in the Y direction. So my expression for the energy equation becomes this one. I obtained this one, this equation, continuity equation, that I call it first equation, the X momentum equation, that is the second equation, and finally the third one, the energy equation. If I do the assumption of negligible body forces, that is capital X negligible, that means for us negligible buoyancy forces, that is valid for the case of force at convection, in the equation 1, that is the continuity equation, and in the equation 2, that is the X momentum equation, I don't have temperature. So if I solve together equation 1 and equation 2, continuity and momentum equation, I'm able to obtain the velocity field. Why, a step back, why I'm writing this list of differential equation? Because I want to obtain, the final aim is to know which is the velocity field and which is the temperature field inside my boundary layer. Solving the equation obtained continuity, momentum, and energy, I want to obtain the velocity field and the temperature field. In forced convection, with negligible buoyancy forces, I observe that the temperature is not involved in the first and the second equation. So if I solve together the first one and the second one, I am able to obtain the velocity field. Velocity field means I'm able to obtain the v component of the velocity and the u component of the velocity. What you obtain here, what you can read in this last sentence of this slide. Solving the equation 1 and the equation 2 inside the boundary layer allow us to obtain the velocity component behavior, the velocity field. And if I know the velocity field, I'm finally able to obtain also the surface stress. Because from the engineeristic point of view, the velocity field is useful because it allows us to analyze the fluidodynamic aspects of the motion and to obtain finally the pressure drop, velocities. Velocities, the pressure drop that can be quantified by means of a surface stress. That depends on the gradient of the u, so knowing the velocity, I'm able to obtain the gradient of the velocity and so the surface stress. The velocity field in forced convection is not dependent on the temperature field. Now I have to analyze the third equation, the energy equation. In the energy equation I have both velocity and temperature. That means that the temperature field depends on the velocity field. To obtain the temperature field is needed the velocity field. So first I have to solve the equation 1, the equation 2 to obtain the velocity field. Knowing the velocity field, I can insert the velocity field inside the energy equation to obtain the temperature field. Is what's written here. So solving the equation 3, I can obtain the temperature distribution and so also information about the convection coefficient H, but the temperature distribution is always coupled with a velocity field, in sense that I need the knowledge of the velocity field to be able to solve the temperature field. This is for forced convection, because for natural convection, also the velocity field is associated to the temperature field, because in natural convection this momentum equation keep the buoyancy forces. We will analyze it later, but I want to anticipate that for the natural convection I keep the buoyancy forces which contain temperature. That means that for natural convection also the velocity field is linked, is coupled to the temperature field. Now I go to the chat to see if someone has written something. I will ask you. Okay. The prof start another. Okay. Wait, I read. Okay. So for I sorry if I can hear you, but your microphone does not work very well. So if you need explanation, then you can write me an email or write me something later. For the other student, it's clear up to this point?
Yes, Prof.
Okay. Because now we do another step that is a bit from the theoretical point of view a bit more complicated. You can say, okay, more complicated than this. Yes, more complicated than this. That means we want to obtain the equations in a dimensionless formulations. And wait, because I have to finally write something. Okay. With the boundary layer approximation, we have this list of new equations that are the continuity equation, X momentum equation, and energy equation in a more simplified way. Okay, we start from this point to obtain another expression for the equations. And in particular, this one to be an example of an approach that can be used not only in convection, but can be used in all the field of physics, that is the dimensionless approach. Some equations can be written in a different way by introducing dimensionless variables. So this approach allows us to obtain, I show you what I want to obtain finally. These are the equations that finally we will obtain, that are absolutely similar to the previous one, but involve dimensionless number, in particular Reynolds number and Prandtl number, which is the advantage to write the equation in this way. Because writing the equation in the dimensionless formulation allows us to create similarity among different cases. Now I'm trying to find more simple words to explain this point. That is not simple. The sense is, for example, if I want to define the transition between laminar flow and turbulent flow, which is the number that I have to use, the Reynolds number. The Reynolds number, and in general, the use of dimensionless number allow us to identify in a more compact way, so using only one number, that is in that case the Reynolds number, to identify a particular behavior of a phenomenon. Without the Reynolds number, to define the transition between laminar to turbulent flow, I have to specify for each case, for each diameter of pipe, for example, for each type of fluid, which is the velocity that gives us the transition between laminar to turbulent. For example, if I have a diameter of pipe equal to 10 centimeters and I have water, I have a particular velocity value that gives you the transition between laminar flow and turbulent flow. If I change the fluid, I have another velocity value that gives you the transition between laminar to turbulent flow. If I change the diameter of a pipe, I have another value of the velocity to identify the transition. Using the Reynolds number, I can give you directly 2200, that is the Reynolds number that gives you the transition between laminar to turbulent flow for all the cases. So in the dimensionless number, Reynolds number, I can include all the information useful to define the transition between laminar to turbulent. So I can give you more information using one unique dimensionless number than a list of different situations. The approach is this one: writing the equation in the dimensionless way using the dimensionless number allows us to obtain and can be used in more situations in a more simple way. I hope to be clear in this explanation. It's not simply to be clear, because it's a very complex case. It's a very complex from the physical point of view. It's not so easy to be understood. It's more or less clear or not?
Yes, Prof.
Okay. Yes, Prof. Okay. So we want to start from the equation, and we want to obtain the dimensionless formulation. We have to, first of all, introduce new variables, because in this case we have x, y, independent variable, then we have the dependent variable u and v, then we have a t, another variable, and so on. We have to introduce new dimensionless variables. And the variables dimensionless are identified with a star. So x star is the new dimensionless variable which starts from x. So x divided by L. L is the characteristic length of a phenomenon. Depends on the particular case. For example, if I'm analyzing a motion, a forced convection of a fluid in a pipe, L will be the diameter of a pipe. So L is in general the characteristic length of a phenomenon. Keep in mind that this case is for forced convection. Forced convection is, you can recognize it immediately because in the X momentum equation you neglect the capital X body force. Then Y star, that is equal to Y divided by L. U star, that is the ratio between U and the U infinite. U infinite is the dimension, is the undisturbed fluid velocity. V star is V divided by U infinite. P star is P divided something that has the dimension of P, so rho U infinite to 2. And final temperature T star is not a ratio between temperature, but is, as usual, if I want to dimensionalize temperature, I use a ratio between temperature differences. And in particular is T minus Ts divided by T infinite minus Ts. Introducing this list of dimensions as variable, I can simplify the equation obtaining this one. Now I want to show you how to obtain. So in the slide you don't have the steps. I show you now the approach only for the energy equation for one case. Then you can try by yourself to write the others. If you have problem, you ask me. So I start from this and I write something now on the whiteboard, on my blackboard. And wait. I have to start un attimo. I change, I go to the paint and write something on the paint. Wait, I have to go where? Okay, let's go. And I have to. Now I have to. Sure. Now you can see the paint, the whiteboard as usual.
Yes, Prof.
Yes.
Okay. Va bene. And I start from the I want to write for you this one. And the dimensions of this variable are so I neglect P because now I analyze only this case for you and P is not useful for me. The approach is the following. Now I show you step by step. I want to obtain I start from the definition of the dimensions of the variable, but then I want to go back to my variables. So I will obtain that by, sorry, and T is equal to Ts plus T star that multiply Ts T infinite minus Ts. So I simply have to substitute in the equation that I write at the beginning the new list of variables. So U will be, here is not me, is you. Okay, and this one will be U infinite U star by dt in the x. So that means t is equal to this one, t infinite minus ts. At the denominator I have x, so x means also L, dt x in the x. Because t is equal to t star t infinite minus ts, so I have to put t infinite minus ts. And L is again, L is here because at the denominator I have I have x, and x was equal to L by x star, plus V is equal to again U infinite by V star, and again the derivative is absolutely the same, T infinite minus Ts divided by L, derivative of T star divided by the derivative of dy star, equal to what? Equal to A. Here I have the second derivative of temperature in y. So I have again temperature at the numerator. So T infinite minus Ts. Second derivative means L to 2, because I have the denominator something that is as dimension of a length to 2, that multiply the second derivative of T star in y star. And I can, okay, starting from this equation, I can simplify it, and I simplify in all the member the T infinite minus Ts, and I can rearrange something, because I can write U star derivative of T star in dx star plus V star derivative of T star in dy star equal to what? I have to divide everything by U infinite and multiply everything by L. And on the second member I keep A, L to 2. That multiply second derivative of T star in dy star. Here I can recognize the something. Now I simplify a length, and A divided by U infinite L. If I multiply both by ni, this ni is, I write better because I want you don't misunderstand. This ni is the cinematic viscosity. Cinematic, I don't know if, wait, I don't know if I have a cave, perhaps. Okay. This one, you can recognize you can recognize the prime number. So you can write in a different way, like this one. This is again me. I go write better. And is me. U infinite by L by A ni. This one is 1 divided Reynolds by Franz. Okay, so I obtain exactly the equation that you find in the slide. So this one is the red part, the coefficient of the second derivative is the second member of the equation. It's clear for all of you? This is only one case to show you the method, the approach. I start from writing the basic equation. I introduce the dimensionless variable. I write the old variable as a function of the new one, and I substitute in the original equations to finally obtain a star equation that include also dimensionless numbers. It's clear for all of you?
Yes, Prof.
Okay, the other student, it's clear?
Yes, Professor.
Okay. And I go back to the slide now. Wait. Wait a moment, because I have again to take my qua con tutti sti anghesi. Wait. Okay. And I go my PowerPoint that is there. Okay. Okay, so in this case, in the slide, I show you only the basic equation. I introduce the dimensions of the variable, and I write for you the final formulation for the dimensionless equation. So the continuity is this one, the x momentum is this one, and the energy equation is this one. Obviously, combined with the equation to be solved, that are the continuity, the x momentum, and the energy equation, I have also to write in the new formulation, that means in the dimensionless formulation, also the boundary conditions. Because keep in mind that we have also a set of boundary conditions with the equations. For the dimensionless formulation, we have to apply new boundary conditions. And the boundary conditions are written here. At the beginning of a plate, what means at the beginning of a plate? Means for x equal to 0, the plate is again this one. At the beginning of a plate means here, for x equal to 0, when for the point for which the fluid is still undisturbed. So the point for which I have still u infinite and t infinite. And I go here. So x equal to 0 means also x star equal to 0. Observing the definition of x star, x equal to 0 means x star equal to 0. So here I have 0 and here I have a 0 because also x star is equal to 0. At the beginning of a plate, I have that u is equal to u infinite and t is equal to t infinite. If I look at the definition of the u star and t star, if u is equal to u infinite means that u star is equal to 1. If t is equal to t infinite means that t star is equal to 1. And here the correct equations. Then I analyze the case on the plate surface. On the plate surface means for y equal to 0. On the surface means y equal to 0. What happens at the surface? I have a no-slip condition for the velocity, so u equal to 0, v equal to 0, and t equal to ts. So y equal to 0 means also y star equal to 0, and I write here y star equal to 0 in all the boundary conditions. And I say that at the plate, u and v are equal to 0, no slip condition. U and v equal to 0 means also u star and v star equal to 0. And exactly is what I can read here. If I'm at the plate, t is equal to ts. What about t star? If t is equal to ts, t star is equal to 0. And so this is the list of the boundary condition at the plate surface. In the free stream means, wait, I have to. In the free stream means far from the surface. For y, that tends to infinity. So in the zone in which the fluid moves as undisturbed. And so far from the plate, u is still equal to u infinite and t is still equal to t infinite. If y tends to infinity, also y star tends to infinity, for which that here in the bracket I read infinity, infinity, because also y star tends to infinity. If u is equal to u infinite and t is equal to t infinite on the free stream, means that again u star is equal to 1 and t star is equal to 1. And this is what I can read here. Okay, it's clear for all of you? And now I want to introduce the dimensionless number, because in this slide you can see the dimensionless equation without having recognized yet the dimensionless number. So here, for example, I obtain a diffusivity divided by u infinite L. But, okay, the process is to recognize the dimensionless number, the so-called similarity parameters that allow us to give more information using one only number than a lot of parameters. And in convection, in forced convection, which are the number that I have to use, the Reynolds number and the Brown number. In fact, we recognize immediately in the X momentum equation here the Reynolds number, and in the energy equation, as I show you with the whiteboard, I recognize the product between Reynolds number and Brown number. And this is the list of a forced convection dimensionless equation for the boundary layer. Wait, because I have to decide if do a small break now. Yes, small break of 10 minutes. Eventually, we will do another break at 12, but now a small brief break of 10 minutes. Okay? See you in 10 minutes. Bye.
Okay, Prof.
Okay, I'm here again. We start again. Are you ready? And I share my screen again, and I want to. Okay. I want to say something. Due to the fact that a lot of students are not still here in Italy and are not still in classroom, it's a great pleasure for me to meet you. If you want to fix an appointment by Teams to know my student, I'm happy if I can know more about my students, because the students in classroom obviously are a bit advantaged because I can meet them. For the other student, I know that is more difficult. So if you need explanation and if you want to ask me something, it's a pleasure for me to know all my students, also by Teams, but personally in such a way, not during the class lesson, okay? And I go on with the explanation, and we were here writing the dimensionless equation with the boundary condition using the Reynolds number and the Brown number. Now we want to obtain finally to obtain the so-called Reynolds analogy, that is this one. The Reynolds analogy, I go now to another slide to show you the idea. We want to obtain finally this Reynolds analogy. Why is interesting and it's important, this Reynolds analogy? The Reynolds analogy allows us, in some particular cases, to obtain the knowledge of the Nusselt number by the knowledge of the friction coefficient CF. That means that in such cases, if I'm able to measure the CF coefficient, I can deduce the Nusselt number from the knowledge of CF. You remember that in convection, the basic law is the Newton law. That is a very simple law. But the problem is really the evaluation of the H convection coefficient, and as a consequence, the evaluation of the Nusselt number. It's complicated, the evaluation of the Nusselt number. In some cases, I can deduce the value of the Nusselt number experimentally if I'm able to measure the CF coefficient. CF coefficient, the friction coefficient, is a measure of forces. I can, measuring the forces, the stresses, the surface stress, I can measure, quantify CF and deduce Nusselt number. So the power of the Reynolds analogy is this one. But now, step by step, we have to arrive to the definition of the Reynolds analogy. So we go back to this slide. And we have to use dimensionless formulation. And in the previous one, I call this one with this symbol, this second X momentum equation with this symbol, and the energy equation with 3 symbols like this one. And from equation first, so the continuity equation, and from the second equation, so from the continuity and X momentum equation, if I do another assumption, that is the pressure P star that does not depend on X, that is the same to say that also the pressure does not depend on X. What was an assumption here written, previously written? If external pressure out from the boundary layer is constant, and for horizontal plate, this assumption is not so strange. It's an assumption that you can do always for a flat horizontal plate. So if the pressure dP x is equal to 0, also the pressure, P star in the x is equal to 0. So I want to simplify neglecting this term. But is a common assumption that I can do. If I neglect this term with the pressure and I observe the continuity equation and the x momentum equation, I can say that the u star component of the dimensionless velocity is a function only of x star, y star, and Reynolds. Neglecting this one, the u component of the velocity, that is the relevant one, what I want to evaluate, is only a function of x star, y star, and Reynolds number. Okay, and I call f1 the generic function that is not known, but is a function that expresses u star. Okay, step by step, shear stress at the surface. Knowing for Newtonian fluids, I know that with a boundary layer approximation, the surface shear stress is expressed only with the derivative of u in y. Surface shear stress means surface means at the wall, so I have to specify that I want to evaluate it for y equal to 0. And I want to express this tau surface shear stress using the dimensionless parameters, the dimensionless variables. And I express again u as u from what I write on the blackboard, on the whiteboard, u is equal to, from here, u is equal to u infinite when multiply u star. So is for this reason that you have here u infinite that multiply the derivative of u star. At the denominator, y is the same. Y is equal to L that multiply y star. So this is again the approach that I show you on the whiteboard. For y equal to 0, for y star equal to 0, y and y star is equal to 0. If y is equal to 0, also y star is equal to 0. And this one is equal to dynamic viscosity, u infinite that is a constant, L that is again a constant characteristic length of a phenomenon, and the gradient of the u star in y star for y star equal to 0 is another function that I call f2 of what? X star and Reynolds. Why only X star and Reynolds? Because if u star was a function of X star, Y star, and Reynolds, the derivative of u star in Y for a fixed Y, if I fix Y because I'm interested in a particular point for Y star equal to 0, so this derivative fixed at Y star equal to 0 is not yet a function of Y star because Y star is fixed is equal to 0. So it's only a function of X star Reynolds number. Okay? And now another step. Okay, thank you. Another step. I want to obtain the expression for the local friction coefficient. The local friction coefficient CFX. Local means that for a particular value of X on the plate, CF change along the plate. Assume not a unique value on the plate, but change along the plate. So is a function of X. Is for this reason that if I at the subscript I write X means that it is the local value of the friction coefficient that change X by X. The definition of the local value of the friction coefficient is the ratio between the surface shear stress tau s and rho u infinite to 2 divided by 2. I substitute here the previously obtained expression for tau s. And I write only, I substitute simply, I simplify what I can simplify, and I recognize here the coefficient, the coefficient of the function 2 as 2 divided by Reynolds, and the fact that 2 divided by Reynolds multiplying the function 2 of X star Reynolds I can call it, I can introduce another function, f3, that is different than f2, that is again a function of x star Reynolds star. Okay? And we keep this slide now for a moment, because now we want to analyze the third equation, that is the energy equation, this one. Again, I can observe this equation, and the equation, energy equation, allow us to say that T star is a function that I call in this case G1, of what? X star, Y star, Reynolds number, prime number. So T star depends on X star, Y star, Reynolds number, prime number. Okay? The same as for U star, observing only in this case the energy equation. If I use the definition of T star, was this one. Remember that for me T star is this one. And using the same approach used on the whiteboard by me, I can write the H expression. And now I go very slow. I want to go slowly because I want you are able to follow me. This first part of this equation goes from something I wrote at the beginning of this long chapter, and now I go back to it. Wait. At the very beginning of this chapter, that is what was here, when I introduced the no-slip condition, I said that in the fluid on the surface, so for y equal to 0, the fluid is motionless. So on the surface, on this infinitesimal layer of fluid at the surface, I can apply also the Fourier Law of Conduction. So conduction, its flux, is equal to convection, its flux. Conduction by using the Fourier Law, convection by using the Newton law. So rearranging this equation, and I want to solve for the H coefficient. The H coefficient can be written as an expression of a gradient of a temperature at the wall, multiplied by the K, the thermal conductivity of the fluid, divided by the temperature difference Ts minus T infinite. Okay, now you remember it? So now I go back to my slide of today. And we were where? We were here. Okay, H is equal to this gradient divided by Ts minus T infinite. Okay, now I want to express again this derivative of T in Y for Y equal to 0 using T star. So again, I have to write T infinite minus Ts that multiply T star at the numerator and L by Y star at the denominator for Y star equal to 0. And I can simplify the bracket T infinite minus Ts also using this minus, because in one case it's T infinite minus Ts, in the other Ts minus T infinite. Okay, and I keep only K divided by L that multiply the derivative of temperature T star in Y star for Y star equal to 0. Now I introduce the Nusselt number. The Nusselt number is defined as H by L divided by K. And as a consequence, is Nusselt number can be expressed only by the derivative of T star in Y star for Y star equal to 0. Remember that star is a function of X star, Y star, Reynolds number and prime number. If I fix Y star equal to 0, I obtain that my Nusselt number is a function of X star, Reynolds and Prandtl number. Okay? So,
Yeah.
I obtained for Nusselt, local Nusselt X, that change along the plate. That is a function G2 of X star, Reynolds and Prandtl. And I obtained that CFX, again, local friction coefficient, is a function F3 of X star and Reynolds number. If I'm interested in not the local coefficient, so not CFX and not Nusselt X, but I'm interested in the average values of Nusselt and C along a plate, so an average value along a plate of length L, the Nusselt average value will be not yet a function of X, because it does not depend on the position on the plate X star, but will be only a function of Reynolds and Prandtl. And the C average value will be only a function of a Reynolds number, not yet a function of X star. This finding is useful. We arrive now at this point that is useful because you obtain the information that the friction coefficient can be expressed as a function of Reynolds number only. And also the average value of the Nusselt number can be obtained by using a correlation which contains only Reynolds and Prandtl. This is important because if you remember from the applied physics, from the courses of a bachelor, the experimental correlation used in forced convection expressed the Nusselt number always as a function of Reynolds and Prandtl. The exponent and the coefficient depends on the case of the geometry of a particular physical phenomenon that you are analyzing. Now, we have obtained a list of complicated expressions, and we want to obtain finally the Reynolds analogy. Up to this point, it's clear for all of you?
Yes, Prof.
Okay.
Yes.
Okay. Now, analogy between momentum and heat transfer. In such cases, we have a similarity between from physical point of view, between the transfer of momentum and the transfer and the heat transfer. So we have also an analogy between the behavior of the CF friction coefficient and the Nusselt number. What I explained before, knowing the CF, in some cases I can deduce the Nusselt number. In fact, if I go back to the dimensionless equations that was obtained here, if I compare the X momentum equation and the energy equation, the equation, if I do the assumption of pressure, gradient pressure in X negligible, so I eliminate this part, and I select fluids for which Prandtl number is equal to 1, I obtain exactly the same formulation for the X momentum equation and for the energy equation. Exactly the same equation. That means if I am able to obtain the solution for U, the same solution is for T star, for U star, sorry. If I'm able to obtain the solution for U star, exactly the same solution can be applied to T star. Remembering that U star is U divided by U infinite and T star is the ratio between differences. So, Prandtl number equal to 1 and derivative of pressure P star in X equal to 0, the equations are exactly the same. The equations are exactly the same, and also the boundary layer are exactly the same. Because if you go back here to the list of the boundary layer, not the boundary layer. If you go back to the list of a boundary condition, also the boundary condition of U star and T star are exactly the same. This one, and this one. So equation the same, boundary condition the same, solution the same. A brief comment to prime number equal to 1. If you remember, I said to you that a lot of engineeristic fluid, so fluid that are used by engineer, that means in our plant, typically water, air, and refrigerants, all these fluids can be considered with prime number in the order of 1, not exactly 1, but if I have prime equal to 3, it's the same as for 1. So the behavior can be approximated as for a fluid with prime equal to 1. It's different the case of oils or metallic or liquid metals, for which the prime number are really different than 1. In the engineeristic fluid, the prime number frequently can be considered as 1, and so I can use this approximation. I can neglect prime number and I can use the Reynolds analogy. What happens with this Reynolds analogy? What happens if I have the same solution for U star and for T star? That also the derivative of U star and T star are the same. So if the solution U star and T star are identical, also the derivative of U star in Y star for Y star equal to 0 is equal to the derivative of T star in Y star for Y star equal to 0. So if I go back to the expression obtained previously, I obtain that, for example, the derivative of T star in Y star is equal to Nussen number, is equal to G2 and Nussen number. If I go back to here, I obtain that du, I can also use, yes, du is the derivative of U star in Y star is what I called F2 of X star Reynolds number. So I go here. I'm sorry, but I have to go back and back to some slide to show you better. So the function 2 is equal to the function g. But the function g, if you remember, is the Nussen number. The function 2 was the C coefficient multiplied by Reynolds and divided by 2, was here. Was this one, yes, this one. The derivative is F2, and so if I want to express it by means of the local friction coefficient, I have to introduce Reynolds divided by 2, what is written, what I have to write here exactly. So this is the Reynolds analogy for prime number equal to 1. That means is what exactly I wanted to obtain for fluid for which prime number is nearly equal to 1. If I'm able to measure, to obtain, to evaluate CF, I can immediately estimate Nussen number and so H coefficient. I can write in another way by introducing another number. So the Reynolds analogy frequently is written in this way, by using the so-called Stanton number. Stanton number is nothing else, a combination of other dimensions and numbers. So Stanton number is the Nussen number divided by the Reynolds and prime number. Using the Stanton number, I obtain this new expression for the Reynolds analogy, but is exactly the same. Okay, it's clear for all of you? And now, if I want to analyze, if I want to use the Reynolds analogy also for fluid with prime different than 1, I can apply a correction based on the prime number. How to introduce this Prandtl correction? The next week, we also on Wednesday, but I don't know exactly if we are able to start with the next Wednesday or next week, but we will study the case of flat plate analytically. So we will solve the equations of momentum and of energy for the case of a flat plate using the so-called Blasius solution. Blasius was a researcher that introduced this approach to analytically solve the problem of a flat plate. From the analytical solution of the convection laminar flow on a flat plate, we will obtain the correlation that you can read here, a correlation for the CF coefficient and a correlation for the Nussen number. These correlations are analytically obtained by Blasius. If I observe the two correlations, the two equations, I can recognize something that is similar to the Reynolds analogy. Okay, so the expression for Nussen, the expression for CF are similar, are linked with an expression that is exactly the previous one, this one, Reynolds analogy, with another correction that is the Prandtl correction. So if I multiply the second member of the Reynolds analogy by Prandtl 2 minus 1/3, I obtain a new modified Reynolds analogy, or also called Kilton-Coleman analogy, that is able to link the CF coefficient to the Nussen number, also in case of fluid with different, for Prandtl number different than 1. Is a manner to generalize the approach for all the type of fluid. Experimentally, it's possible to show that this analogy is valid also not only for laminar flow, but also for turbulent flow over a surface. So also for turbulent flow, I'm able to deduce information about the Nussen number by measuring, by estimating the CF coefficient. It's not possible to apply this analogy for a fluid that flows inside a pipe. Okay, is valid only for the case of a flat plate. Yes?
On the slide, I have that the Shear number has to be bigger than 0.6.
Dove è scritto?
On the slide.
Ok, forse quelle stampate. Dove l'avevo messo? Wait a moment, because a student asked me something in class. The only student that is in classroom. Okay, yes, you can neglect it because now the student asked to me why you have a limitation in the Prandtl number near to the Nussen correlation on this slide here. Is something that comes from the solution of Blasius, but at this moment, when in the new version of the slide, I neglect it because I think that can confuse it. Okay, it's clear for all of you?
Yes, Prof.
Okay, va bene. Now we have to. Aspettate un attimo che guardo cosa ci aspetta. Va bene. So today, now we have in this chapter, we have this part that is drag force, that is okay. Something not so important, but we will analyze this part next lesson on Wednesday. Now we go directly on we have a lot of time this morning, and we go to something about the turbulent flow. So on Wednesday, we go back to the drag forces, and we will study the correlation on Wednesday. Here, turbulent flow, okay? Because now I think that is more useful for you to now analyze the turbulent, this part of the turbulent flow. So we finish with the equations and then we go to more simple, not simple because then we have also Blasius solution that is not simple, but we can imagine to do some exercises on Wednesday. I have to organize better. Now, turbulent flow, and then we finish for today. Turbulent flow. We know that we have two different regime of possible fluid flow, the laminar flow and the turbulent flow. Turbulent flow is still unknown. That means we have a lot of researchers that study turbulent flow, but the theory is not clear. Not yet clear because it's a very complex phenomenon. So we have a lot of theory, a lot of studies, but it's continuously changed and continuously updated the theory about turbulence. In this part, I want not to explain you completely the turbulence, obviously, but to give you some ideas about the different approach that we can use to analyze turbulent flow. And which is the number, the dimensionless number that allow us to define the transition between laminar and turbulent flow. Obviously, you know that is the Reynolds number. In laminar flow, what happened? We have ordered motion. The fluid moves mainly in a direction that is parallel to the surfaces. That means if I move on a flat plate, I have the motion that is in the x direction mainly. And so u component of the velocity. In a pipe, I have a motion that is mainly parallel to the surfaces of the pipe. Why I have this inline ordered motion? Because if the Reynolds number is small, means that the viscous forces are bigger than the inertial forces. And that means that the viscous forces keep the fluid in line, ordered. If I increase the Reynolds numbers, and the Reynolds number increase if I increase, for example, velocity, the inertial forces become more important, more relevant, and become also bigger than the viscous forces. That means that the eddies can create inside my velocity field the other component of the velocity, u component of velocity, not parallel to my surface, become relevant. And I have a fluctuation of the velocity field, and so the creation of turbulent flow, which is the mathematical approach, so the theoretical approach for the turbulent flow. I have two represents this eddies motion and random, that is a random motion. I combine for each property of my system, of my phenomenon, two components. So the property P, the generic property P, can be expressed as the sum of the average mean value of the property P plus its fluctuating component. Here in this sketch is more clear. That means the property P in time. P represents the average mean value of this component, but this property fluctuates because I'm in a turbulent flow, so I'm a random fluctuation of a property, and I have to add to the mean value P with average, yes, average value, a fluctuating component that changes continuously. The mean value is calculated, must be calculated over a time interval that is large enough to neglect the fluctuation component. That means if I, for example, take the average of P for a too small time step, I do not have I do not have really the average value, but I have too much of effect of fluctuation. I have to select to do the average value to obtain the mean value of the property to take into account enough time. In this enough time, I have that the average effect of fluctuation is 0. That means if I write P first, the average value is equal to 0 in the time analyzed to obtain the average value, the mean value for my property. If I speak about steady flow, steady turbulent flow, which is the sense to speak about steady state flow in turbulence, in which I have all the properties that are fluctuating. Obviously, nothing is steady really in turbulent flow. When I speak about steady turbulent flow, means that the mean value of a property are independent of time. Obviously, the fluctuating component is always depending on time, but in steady state turbulent flow, the mean values are independent on time. And with this introduction, I can write the equations and turbulent flow equations. Again, I want to consider the two-dimensional case. Steady turbulent means that if you look here at the variables, at the list of the variables, I have the first row contain the mean values of the variables, and the second row contains the fluctuated component of the variables. Steady flow means that the mean value of the velocity u, the mean value of the velocity v, the mean value of the temperature is not a function of time. This means steady state in turbulent flow. Obviously, fluctuated component depends on time. I consider only fluctuation for velocity, u and v component, and for temperature. Negligible fluctuation for the thermophysical properties. So I consider as constant the density, the specific capacity, the thermal conductivity, and the viscosity. If I use this new set of variables, I do not show you all the steps to obtain the final equation. You have only to know that in steady state flow, I have to use this set of new variables. Using the boundary layer approximation that are absolutely similar to the boundary layer approximation presented to you for the laminar case, I obtain this new set of equations that are shown here at this slide. If you observe the equations, the equation is absolutely equal to the previous one, to the case of laminar flow, but in the x momentum equation and in the energy equation, I have a new term in this bracket, which depends on the fluctuating component. Up to this second term of the bracket, I have an equation that, written in the mean values of u, of v, of p, is absolutely the same as for the laminar case. And also from the point of view of the energy equation, if I neglect this second term of a bracket, I have an energy equation that is exactly for the laminar flow, taking into account again the average value, the mean value of the velocity, of the temperature, and so on. Okay? Which is the sense of the second term of a bracket inside the x momentum equation and inside the energy equation? Is the effect of fluctuation, is the effect of, obviously, of the turbulence. And how to represent and to quantify it and to include it inside the solution, because finally we want to solve the problem. We want to obtain, as for the laminar flow, we want to obtain the velocity field and the temperature field to be able to quantify then the shear stress that means the pressure drop, also from the generosity point of view, is the pressure drop that I want to evaluate, and the transfer rate, the H coefficient, and then the transfer rate inside my system and my phenomenon. And I define an effective shear stress and the effective heat flux. And I divide the effective shear stress and the effective heat flux in two parts, the laminar component and the turbulent component. So this bracket includes two contributions. The first one, that is something that is similar to the laminar case, and the second contribution that depends on the turbulent behavior, the same for the energy equation. In particular, I call effective shear stress tau IXF, that means effective, exactly what I have in the bracket. Exactly this laminar shear stress and the contribution which depends on fluctuation. The same for the heat flux. The heat flux is expressed as the Fourier law at the wall for the laminar contribution, plus a contribution that is the turbulent one that depends on the fluctuation component. Boussinesq, that is another researcher that we will find also when we will study natural convection, because we will study natural convection using the so-called Boussinesq approximation. Boussinesq studied also the turbulent flow and introduced a new coefficient that he called turbulent cinematic viscosity and turbulent thermal diffusivity, Ni-T and AT. This is at the bottom of the slide, the definition of the turbulent cinematic viscosity and the turbulent thermal diffusivity. Obviously, they are a function of the fluctuating component. By introducing, so we can express the second part of the effective shear stress using the turbulent cinematic viscosity. So if I want to, I simply substitute inside this part, the second term of the shear stress, this expression which contain this parameter that is the turbulent cinematic viscosity. Similarly, in the expression of effective heat flux, to express the part associated to the fluctuating component, I substitute this expression that introduces the turbulent thermal diffusivity. And what I obtain? I obtain something that is something like that. I obtain this expression in which I have a bracket which contain the Mi is the dynamic viscosity, that is a thermophysical property of a fluid, plus something that is not a thermophysical property of a fluid, because the cinematic viscosity turbulent, so Ni-T, is not a thermophysical property of a fluid. It's something which depends on the motion. Is something which depends on the fluctuating component, so depends on the phenomenon, not only on the fluid. Is not a thermophysical property of a fluid. The bracket multiplied by the derivative of the mean value of the u component of the velocity in the y direction. The same for the heat flux, effective heat flux, in which the gradient of the mean value of a temperature in y is multiplied by the effective thermal conductivity, that is the sum of the thermal conductivity, thermophysical property of a fluid, plus something that is not a thermophysical property of a fluid, because contain AT, that depends on the motion, depending on its definition, which depends on the fluctuating component. A comment about these two equations. In the core region of a turbulent boundary layer, so if I'm inside the boundary layer, inside the turbulent boundary layer, which is the main contribution, the turbulent one or the part that is a thermophysical property of a fluid. Obviously, it's much more relevant this part, the turbulent one, both this one and this one are much larger than their molecular counterpart. So I can consider mainly the effect of turbulence. Close to the wall, so in the region near to the wall, due to the no-slip condition, the motion is again in line, more in line, is what in Italian we call sottostrato laminare. Perhaps you listen about something like that. When I study a turbulent flow and when I define a turbulent boundary layer, near to the plate, I have the creation of a small layer near to the plate that behave like in laminar case. A sublayer laminar, in Italian is called sottostrato laminare, that can be translated as laminar sublayer, that is a thin layer near to the wall, in which the eddy motion diminishes, and I have more relevant effect of the molecular counterpart, that is K and me. Remember here the sense at the end, Nt, At are not fluid property, and because they depend on the flow condition. With the introduction of these new parameters, I can write this list of equations in a new form. That is this one, the Reynolds Equations, in which I have that the second member of the X momentum equation and the second member of the energy equation include in using this μF and kF also the effect of the turbulence. How to solve this type of equation is not simple, because we have not the same variable as previously, because we have obviously U average value, V average value, T average value to be evaluated. So this one, and this one, that are the variables similar to the laminar case. But now we have also to estimate the turbulence effect. So we have new variables. It's a system of 3 equations and more than 3 variables, which are the so-called turbulent models. Turbulent models are nothing else, different approaches to solve the problem of turbulence that add to the Reynolds equation. The Reynolds equations are the one listed here. Add other equation to the free Reynolds equation to be able to solve a system of equations. And we have different possibility. The first one is the zero equation model. That means the mixing length model is not a zero equation, because obviously we need one equation, one expression to be coupled with the previous one to solve a problem. It's called zero because it's not a differential equation that I add to my system. Is something else. Is a correlation that include the mixing length. No, is not the sense of this lesson to introduce to you the models. We have different approach. The first one is the mixing length model, the more simple one. The second one is the so-called n equations models. N means the number of equations that I add to the previously Reynolds equation to help me in the solution. And we have key epsilon model, key omega models, and so on. A lot of models that you can find, for example, in the softwares CFD solution, in turbulence you have a lot of models that you can select to approach the turbulence problem. Interesting is this one, this point, that I can define a turbulence Prandtl number. As for the laminar case, I have two problems: the fluid dynamic problem that allow me to find the velocity field, and then I have the thermal problem that allow me to find the temperature field. The two solutions are linked and can be linked also by linking the turbulence diffusivity and the turbulence kinematic viscosity. If I define a Prandtl number, a turbulent Prandtl number, which is the ratio between the turbulent kinematic viscosity and the turbulent diffusivity, solving, for example, finding me, if I know the Prandtl number, I'm able to estimate A. And is the case. Frequently, we assume that the Prandtl number, Prandtl turbulent number, is equal to, for example, 0.87. By knowing that is 0.87, I can solve for example, μt, and find deduce AT by the knowledge of its Prandtl number. But really, the sense is not to show you the models, the turbulence model. The sense is to show you which is the approach, which is the, in turbulence, we have two types of parts in the same property, fluctuating and mean average value, and the introduction of the effective shear stress, effective heat flux, with a part that is linked to the fluctuating component. Finally, we have this is last slide that show you the shape of the laminar and turbulent boundary layer. Okay, we have that. This is the shape of a velocity profile for laminar flow. This is the shape of turbulent flow. If you draw also, if you want to represent the gradient of the UV component of the velocity at the wall, that depends on the surface shear stress. You remember that the surface shear stress can be expressed as a function of the gradient of the U component of velocity in Y. This value, if compared to the same derivative for the turbulent flow, obviously for the turbulent flow, the derivative is of U mean value. This turbulent flow, for the turbulent flow, is much bigger than for laminar flow. That means that pressure drop, and the same is for the gradient of the temperature, is bigger for the turbulent flow if compared to the laminar case. That means that if the two gradients are bigger for the turbulence than laminar, both the wall shear stress and both the heat flux at the wall are much bigger in turbulent flow than in laminar flow. So it's a manner, this slide wants to help you to visualizing the velocity profile and visualizing the gradient of the velocity, and imagine the same approach for the temperature gradient. Why I obtain more pressure drop and also more transfer rate, hopefully, for the turbulent flow than for laminar flow. It's clear? Ragazzi, siete svenuti?
Yes, Prof.
Siete svenuti?
Yes.
Okay, so it's prestissimo. Okay, I prefer to stop now. Okay, because a lot of information, not so simple to understand, and I prefer to stop, not to explain more, because I think that otherwise it's not so clear for you. It's okay if you have questions? No? Okay.
It's okay, Professor, but I think we are going too fast.
Going too fast. Okay, no problem. But you can stop me during the lesson. Otherwise, I can imagine that it's too fast. So I take into account your observation. Thanks, but stop me before. Okay, if you think that I go too fast, stop me during the lesson so I can go more slowly. Okay. If nobody said to me nothing, I can see your face during the faces of a student during my lesson, because you are not in classroom. So when the students are in classroom, it's more easy to me. I observe the faces and I can deduce if you are able to follow me. In this way, I can see anybody. And so if nobody stop me, I go on. Help me during lesson to say, Professor, repeat, or Professor, more slowly. Is not a problem to me. Otherwise, as usual, I'm here for explanation if something is not clear. Thank you very much, and have a good day. See you on Wednesday. Bye.
Thank you, Professor.
Bye, Professor.
Bye.
Thank you, Professor. Bye.